Welcome to Algebra, Solving Systems of Equations, Part 2, Substitution and Special Cases. In the last lesson, we learned about how two linear equations create a system of equations and that the point where those two lines cross on a graph is called the solution. We found the solution by graphing and by doing some algebra. Now we will learn another way to find the solution called substitution. We will also examine some special cases that you can find when solving systems of equations. Let's do a quick review of what we learned in the last lesson. Here are two equations representing lines on a graph. Neither equation is graph-ready, since slope-intercept form y equals mx plus b is the most direct way to graph an equation, especially using an online app like Desmos, which you will be able to use when you test. We convert both equations into that form and graph them to find the solution to be the point 5, 7. Another method to achieve the same solution is called substitution, and is often the better process if converting to slope-intercept form for graphing is not the clearest way to the solution. Here, you can see the first equation shown in slope-intercept form with the y variable isolated, y equals 2x minus 3. But the other equation is not, and converting it to slope-intercept form does not make it easy to graph. The b value, the y-intercept, is the fraction 13 over 4, or 3.25, and that value does not locate well on the y-axis at a clear point, making the graphing approach not as easy to do. When this is the case, you can use the substitution approach by replacing the y variable of the other equation with the right side value of the first equation, since that is equal to y. You are replacing the variable y with an equal value. The value of y is 2x minus 3, and that can take the place of y in the other equation. Now use your algebra processes to solve for x. First, distributing the 4 on the left side, collect the x terms on the left side and the constants on the right, divide by the coefficient of x, and find the value x is 5. Now substitute the value of x back into the first equation to find the value of y, which is 7. This matches the solution we found previously by graphing using Desmos. Here is another system to solve. First, we'll use graphing to find the solution, solve both equations for y, graph each, and find the point where they cross, 7, 2. Notice neither equation in slope-intercept form crosses the y-axis at a clear point, so trying to graph this by hand would be difficult to do. Using the same system, we can solve by substitution. This time we can see the x variable isolated in the second equation, and so we can substitute for x in the first equation. Using distribution, combining like terms, collecting variable terms on the left and constants on the right, and finally dividing by the coefficient of y, we find the value of 2 for y. Substituting 2 for y back into the second equation finds the value of x to be 7, the solution being the point 7, 2. Just as we found it by graphing in the previous example. Although this process does take a bit more work, often it produces a more accurate result than graphing would do, especially if you have to do the work by hand. Here are two more equations, and we can see the result of first converting both to slope-intercept form to enable the graphing process. One of them does cross at a clear point, 0, but the other one does not, which makes graphing by hand much more difficult to do. We use the substitution process with this system, replacing x in the first equation with 3y plus 5 from the second equation, solve for y to get 4, and then replace back into the x equation to find the value 17. This matches the solution we found by graphing. Finally, we need to discuss some special cases you may encounter when attempting to solve certain systems of equations, just as we saw in an earlier lesson about one-variable equations. We learned that there may be no solution for an equation, or all possible values as solutions, all real numbers. The same can happen with systems of two variable equations representing lines of x, y points. Essentially, there are three possible solution types when solving a system. All the examples we've studied so far have had only one solution, one point where the two lines intersected. It is also possible to have no solutions, no points where the two lines cross, or all real numbers where the two lines have all points in common. Think about it for a moment and see if you can come up with a general idea of when these two special cases could occur. Here are some examples of systems with one solution, one point in common, one point where the two lines cross. We've seen several examples of this already. Have you come up with an idea of when there might be no solutions? If you thought, when the lines are parallel, you are correct. Parallel lines never cross, and so there will never be a solution for a system of equations that represent parallel lines. How about the solution of all real numbers? If you thought about two equations that represent the same line, you are correct. It is possible to have two equations that are in different forms that represent the same line. A solution of all real numbers means that for every possible value on the x-axis you can plug into either equation, the y value will be the same. The two lines match exactly, point for point, all the way into infinity and beyond, in both directions.